So these days, seems like everyone's trying to do automation, different things, right? We're trying to automate art. I don't know how many of you have seen this. This is like DALL-E 2. Yeah, so you can put in some text and it will make a picture, painting in some kind of style. You could change these up to any combination on their website. It'll give you a different one. I'll just paint it for you. They're trying to do self-driving cars. Okay, this one is a cruise car, right? It's got all sorts of different sensors sticking out in various places. I'm not sure how good they are, but they are getting more permission to drive in larger and larger areas of San Francisco, doing more of it. People are trying to make AI. Not really sure of a good picture to put, so I asked DALL-E 2 if you'd ask it for a human basking in the sun of AGI, that's artificial general intelligence utopia. So this raises a question, can we do it too? Why not try to automate statistics? I mean, I think that is answerable with a couple of good reasons, by the way. Do we trust people with all the tools we've given them today? But where I'm working, I think it would be a very useful thing. Things get genuinely very complicated. If you were to start with, say, a standard clinical trial of treatment versus control, people want to add on more and more things. Maybe there's 3 treatments and not 1, and you're trying to, find not only, say which one's the best, but after 6 months, you want to drop 2 of the treatments and keep going with the better one versus control, get better inference on that one. Maybe there's a delay, a lag time in recording, right? When the patient's deaths are observed or progression of disease. There are operational constraints that come up. So maybe the 3rd treatment arm is going to start late. Okay, let's make it even more complicated. Let's give randomization probabilities, which now change between these arms. We can have an algorithm for doing that. Maybe it's given to us. Maybe it's something that we should be deciding. Maybe our goal here is not only to maximize the information we get from the trial, but also the welfare of the patients as we're doing it. Oh my goodness, what a headache. What is the optimal experiment design and significance test? Good luck. Okay, and these are the problems that I've been wanting to solve, banging my head against them with pencil and paper, not getting all that far. My advisor at CLI did wonderful things and various combinations of these things. But I begin to wonder, has he taken all the easy low-hanging fruit? What's left for me? I think computers have a good shot at adapting to these hard problems a lot better. The optimal solutions for these things are complicated. They should be complicated. And if we want to handle that, we have to computerize, which raises a difficult question now. If a computer were to hand you the optimal design and the optimal inference, and let's say it even controlled the type 1 error, which was something that you wanted, right? Could you even recognize it as doing that? So I guess one way to say what I mean by like automating the statistician is we could break this down to a bunch of steps, perhaps, right? If we want a whole pipeline here, where we input the problem setup, some model of the world, some model of the universe, what do the possible outcomes look like for our patients, possible prior on our treatment effects, perhaps. We're going to need to design an experiment. We're going to want an analysis chosen. We want sometimes some type of guarantee or validation, right, about what we've done. And then at the end, we're going to have to persuade people about what we've done. What we're going to do today is just a part of that. We're going to focus on that guarantees and validation step, with the goal here that we can help experts do more, do better, reduce mistakes, but also permit more automation in these steps 2 and 3 here. So that if someone were to show up with a really black box design something complicated going on, you could say, yes, this works. So we're going to ask for a number of things in order to try to approach this. We're going to require here some pre-specified experiment and analysis plan that we're going to say we have access to a simulation of it. We're going to require that our outcomes here are exponential family. We're going to need some bounded region of space that we care about. If it were infinite, okay, that's an infinitely large computational problem. Let's make it finite, and let's make it finite specifically in that exponential family's natural parameter space. And we're going to need a lot of computational power. So for a given number of unknown parameters here in our exponential family, it might cost different amounts. These things trade off against each other. Fundamentally, what we're doing is we're trying to blast through the curse of dimensionality with Moore's law. So there's trade-offs here, how hard it is to simulate your design or how many parameters you need to go over, right? That translates to the computational scale, or maybe the time you'll need to wait for Moore's law before you can tackle that problem. What we're going to ask here, out of this is we're going to try to aim for a rejection threshold, some procedure that controls the family-wise error rate. Oh, I guess this should say alpha, less than 0.05, but you get the picture. I think you could use these tools for other things as well. Confidence intervals, maybe FDR control, bounding the bias or MSE of an estimator with the same techniques. We're not going to talk about those topics today, but I don't think it's a very hard generalization to get there. Let's see. Yeah, all right, we're focusing on this. Beyond clinical trials, which are where I work, I think there are other things you could do with these types of techniques. If you want to have some black box experiment neural networks making the design decisions for you of your rejection procedure, say, you could try to feed it through this. If you want to take a Bayesian procedure to be your black box, maybe you could tune it to get frequentist type 1 error control over it. If you're doing a multi-armed bandit problem, maybe you could get family-wise error rate, FDR guarantees. Maybe for the lasso, this is still speculative, but I think it could be possible that under certain strong assumptions, you could get inference for the lasso. Ugly problems like HMM models, where the amount of sampling that you get is depends on the parameter setup. Maybe you could do confidence intervals for that. Or stuff like the Behrens-Fisher problem, where you might think that you want to get a little bit of edge over, say, the Welch's t-test. How could you actually establish that this is happening if what you cooked up to improve it was just a bit of tweaking? Okay, so we're building software for this. James Yang has done a fantastic job of building this out into a real computational framework. We're just getting started. We open sourced a couple of weeks ago, but we've got some prototype up with a few basic examples aiming at the clinical trials side. Okay, but let's not start there. Let's start with a very basic example. So the most basic test you could have. Let's consider that we've got a normal testing problem, normal mu, right, with testing for mu with a sigma squared equals 1. We've got our null hypothesis being that mu is less than or equal to 0. You want to have a budget of alpha equals 0.025. And we're going to look at this region near the boundary of the null hypothesis. Let's zoom in there. And we're going to make an assumption here. This is not meant to be realistic, but let's idealize and say we had some infinitely powerful simulation which gave us the exact type 1 error at 2 specific points here in our diagram. We can ask, are we going to be able to show, if you were given access, say, to the z-test for this, right? Would you have a strong claim that it's controlling the type 1 error? Probably not, right? Maybe the type 1 error function could be wiggly in between going up above 0.025, coming back down. Okay, and that would be problematic. We want to make sure that that's not the case. All right, so I guess we should add a little more information. Well, we can assume that we know a little bit more. We can assume that we know the true derivative of the type 1 error as well. That's going to get us a reasonable approximation, actually, although not a conservative one. Right, we're still in this case below the true type 1 error line. But this error here on that first order approximation, we can describe that by Taylor's theorem. So we could say if we had some bound on the second derivative of this type 1 error function, we should be getting a conservative approximation. Now, this is not a particularly good one. We wanted some upper bound that would keep us below 2.5% for this procedure. We got something like 0.04, 0.05. Okay, not so good. But what we can do, maybe just double the number of simulation points, and it will look better and better until the approximation is good. So by reducing that grid spacing, right, we pay a vanishing amount to this second order term. So there's a number of things here which doesn't translate exactly over to real problems. The first thing is that this is, well, first of all, one-dimensional here, right? This is a bit simple. And so that would be a slower phenomenon if you had larger dimension. The other thing is that this type 1 error at these certain points, you won't know exactly, but you might be able to simulate with Monte Carlo. So you'd have some maybe confidence interval around each point for what the type 1 error is. And let's also, for now, just assume that we can do something similar for the gradient and come up with a confidence interval for that as well. So if we combine these, we could come up with some kind of 1 minus 2 delta confidence interval for the first two terms of that Taylor expansion. And then if we were to just add on top of this, I don't have a nice graphic for it, but add on top of this the parabola, okay, then we'd have a confidence set, which should hopefully not have a maximum that's too large. And at least as these confidence bounds shrink, you'll be getting a better and better bound on your procedure. So here's an example of doing this on, if you were to take this simple example, say for the z-test here, and double it, do it twice for two independent arms. This would be, you're looking at a display of the true family-wise error right here as a function of the unknown means, right? You can see it just zeroes off once we cross 0, right? The worst case is where they're both right at that boundary. And we could run this type of method on it as well. You'd be recovering a similar sort of shape. There'd be some noise we are simulating. And so, it's not exactly right going to be a nice curve like this. There's some simulation error and also some loss. But hey, that's not too bad. And it turns out we can also use these techniques for very complicated designs as well. So this one is actually super complicated. This is, I don't know if you all are familiar with Thompson sampling. It's a common thing in like the multi-arm bandit literature and Bayesian clinical trials, where here, let's assume we've got, say, 100 cancer patients, perhaps. We're randomizing each one of them in sequence between arm 1 and arm 2. As we go along, we're updating, we're taking in information and using a decision rule based on posterior probabilities to decide the chance of giving the patient to each arm. This is really complicated. I don't recommend that you try to understand this mathematically. Some people have done some work on doing this. I think Stefan Wager has a paper of trying to understand the limiting behavior of this stuff. But still, hey, this is actually technically finite sample, although it is conservative. So this is a rather large computation. In order to get this, I was doing almost 1 million simulations at every point on this grid, 16,000 grid points. That's like 10 to the 10 simulations. Okay, so I had to work a little bit in order to make things fast, right? Take it to Sherlock. And now, well, actually, if I have, James is much better at these things than me, he could do it on his laptop, now after working on it, but still, right? We do need some scale to make this nice. Okay, so broadly speaking, these are the sorts of steps that we're going to do then. We're going to say that our type 1 error function is some function f. It depends on theta, which is an unknown parameter, a vector, right? We have an exponential family with that as our natural parameter, let's say. We're going to break up our space that we want to cover and give a family-wise error rate guarantee over. We're going to break it up into subrectangles. They're going to be centered at these different points. Okay, and for each one of those gridding points, we're going to do a Monte Carlo simulation, make a Monte Carlo confidence interval for the type 1 error at that point. We're going to try to do something similar for the gradient at each point. We're going to find,
What's a definition of a Monte Carlo simulation?
Here, I mean that we have access to simulate what the design is going to do. So I think of this as being, say, there is some true theta out there, right, in nature. We don't know it, but if, and say I've gridded out the space of possible thetas, right, to go into my exponential family. If it were the vector, arm 1 has a 30% chance of success, arm 2 has 50% chance of success, I could go to my computer, simulate out the result of the trial, right? So it will play it through. It will result in a rejection decision, right? And either that will be a false rejection or not. And so that process, right? And, Monte Carloing out what is the type 1 error here is what I mean. So once we have these quantities here, right, we have this confidence interval for the base type 1 error, right, at these different points in our null hypothesis space. We have a confidence interval for the gradients of those same points. We're going to want some sort of uniform bound on the second derivative within each subrectangle. And we want to maximize this over each of these rectangles individually as a subproblem. And my claim here is that this gets you a 1 minus 2 delta upper confidence bound for the type 1 error function. Okay, this is not a uniform upper confidence bound, it's a pointwise one. That's okay, that's what you want, because there's only going to be one true theta in nature. Okay, so for that particular theta, this is going to be valid. That's all we need. Can you spot the issues? Hands up if you can see a problem. Here, I'll go back. There's a couple actually. Yeah.
About how you estimate f theta,
Mm-hmm.
not the gradient.
Okay, good. I'll talk about that later. Any others? Yeah.
Maybe grid space gets exponential.
Absolutely, that's a problem. Great. Any other problems? Oh, okay. So yeah, maybe you've taken too small of a grid and you haven't covered all the relevant space. That's a problem. I don't have a general solution to that. What people do, hopefully in clinical trials, is just take a reasonable range of plausible parameters, because presumably the treatments we're giving people aren't just straight killing them. But indeed, yeah, it would be nice to have a general purpose arguments for that. I don't have that. I have only certain, there are ways to get these bounds in certain cases, but not a fully general approach.
Can the maximization be tricky? Maximizing with the expansion?
That is surprisingly not that bad, actually.
Because it can be like non-concave.
So if you were to take a worse shape than a rectangle, you'd be in trouble. Rectangle is fortunately easy enough. There is one serious issue still.
Would the serious issue be gone if this grid was very, very fine? I mean, as the grid gets finer with this.
So yeah, that's the solution to the conservativeness problem, right? Or at least as you increase the computation. But here's a hint I'll give then. Let's say that we were targeting some specific type 1 error rate and we want it to be under it. The rejection could be rare. Well, okay, if it's too rare, then we can rule it out essentially, right? So it should be okay. But really what I'm fishing for here is this list of problems. You guys got number one. This upper bound is indeed conservative. Two other problems. Number one, maybe you're unsatisfied about the fact that, okay, we have a confidence statement about a statistical design rather than just a full proof, right, of the whole thing in one shot. And the last one is perhaps the trickiest issue, which is that Monte Carlo is random. And so if I had a design that actually controlled the type 1 error, I might fail to verify this, right, consistently, depending on, how I'm running it, right? I could just get bad luck in my Monte Carlo. That's not so great. So we have some solutions for these. So the first one, the fact that it's conservative, well, I will hand wave that and say Moore's law will take care of this. Maybe it will, maybe it won't. And for large and difficult problems, it certainly won't. But for, over time, things get better. If you use a finer and finer grid, right, the Taylor expansion gets more and more accurate. If you increase the Monte Carlo simulation sizes, right, your width of conservativeness there gets better. The way I guess I'd suggest to handle the second issue would be, if you wanted some, I should have said again, alpha less than 0.05, rather than having a confidence statement about, alpha less than 0.05, just make it about alpha less than 0.04, right? And tack on that, extra little amount as a penalty. Okay, this is a bit conservative to do, but still, you won't be, you'll be keeping within type 1 error constraints when you do it this way. Maybe need to, increase the computer simulation size a little bit to pay for it, but, if we assume unbounded computing power, this would get reasonable as we took that delta to be smaller and smaller and smaller. We just kind of don't care. The last issue we do need to fix. And my proposal here would be that we don't anymore consider our procedure as just a fixed procedure, but we try to tune it. We put it within a family of procedures as if we've got, say, a critical value. And let's index it now by some parameter lambda, which gives us a whole family of rejection procedures. This could be, for example, just if you're using z-test, for example, this could be the critical threshold you use. What we need about this is just that if you shift along this family, right, you are monotonically increasing or decreasing the rejection set. And the claim I make is that if we have a discrete sequence of these different procedures, right, from sort of smallest to largest rejection set, and we're looking in each case over for each of these procedures at the worst case type 1 error in the null hypothesis set, and specifically looking at our upper bound in it, we can look for the point where we're going to first cross 0.05, stop right before it, and use that lambda, and that this is going to control the type 1 error as an overall procedure. Okay, we're going to go back again through the technical details of most of these things, not this specifically, but the other stuff. But I suppose it would be a good time to take questions on just the general framework of what we're doing here. Yeah.
So if you have a fixed computational budget, does it make sense to use the same number of Monte Carlo simulations for each region? Or could you more intelligently distribute your computation to those regions where
Yeah.
you're about the upper bound?
Certainly that makes sense. We started trying to do that. And I'll show you some results of that actually towards the end.
Is this monotone sequence also possible when you have multi-parameters?
So yeah, in this case, you will need to have this single monotone dimension affect all of the rejection procedures, for each of the arms simultaneously. So this needs to be monotone on the rejection set generally. So the type of thing that I would think about here as being a reasonable choice of rule, for example, is, for multi-armed problems, we typically might want to use a Bayesian procedure to do the rejections, often in terms of that there might be, say, a critical threshold of the posterior probability, okay, where if we have a 95% chance that the arm parameter is greater than our critical threshold, we reject. That 95% is something that's tunable. And so if you shove it up and down for every arm, that now gives you a monotone family if you're doing it for all of them jointly. There is a little bit of discomfort. It's true that this is not necessarily, I don't have a nice multi-dimensional version of this, right? But fundamentally, it's because, the family-wise error rate is a sort of joint quantity of all of these things. It might be possible to say better things about that scenario. I just haven't. Okay. So our setting here, we're going to require here that we have an exponential family. It's a big class still, right? Gaussian things, binomial things, exponential, gamma, y-pole, okay. This data likelihood, we're going to assume, right? We can sample adaptively. So based on what you've seen so far, you can choose to either stop at time tau or keep going. We're going to say it's also okay if you have sensor likelihood. I haven't written that here, but it would be okay in the sense that, since we're handling these things with simulation, that's sort of like a beneficial de-randomization. Although I'm not going to work through the details of that. The nice thing about exponential families as well is that, okay, if you can handle them, think of this as a process, right? Lots of things have limiting Gaussian behavior. And so you could do this with Brownian motion as well, right? Things which have a limiting Brownian motion, although you would be losing the exactness. So going into our Taylor expansion here, we're going to take this guy in remainder form. Right, we're going to say that we have this vast grid of different parameter values and regions of space that we want to cover around them. Right, we're going to write this type 1 error function f here in this way. Okay, so this is the type 1 error, the true type 1 error at that point, the true gradient at that point, right? Transpose multiplied with your distance as a vector. and then this second order thing. Our strategy here is we're going to treat these terms separately, split them up, and then maximize them over our rectangle space that we're trying to cover. So then the proposal for the first term, run a million simulations, perhaps. It's about what it takes if you say are looking for a type 1 error, below 0.05, 0.025, and you don't want a very large standard error that's consuming a lot of your value of your bound. Okay, and the type 1 error here that you estimate here from that simulation is going to be Bernoulli for each IID simulation. We can make a binomial interval here. Klopper-Pearson will do the job. That's not too hard. Hey, question from before, right? What do you do for the gradient? And so if we assume that we are in, oh, by the way, something I didn't mention before is we needed smoothness of the likelihood in order to do this. Will require that our rectangles are not jumping across intersection hypothesis regions, that we're within the same intersection hypothesis every time. There are still things you can do if that is happening. We're not going to worry about that though. We're going to right now say then that this set F, given a fixed intersection hypothesis, right, describes the set of false rejections. So it now depends only on the data, essentially, that we observe. And this gradient of the type 1 error probability, right, sort of writing this out as an integral, if you pass through that derivative into the exponential family likelihood, it pops out with this extra sort of weighting factor here, essentially, where we have, again, got the exponential family likelihood once more, and this extra little bit. So then my claim here is that you can get an unbiased estimate of this gradient at a fixed value of your parameter if you just take that weighting factor and average it. This weighting factor being here, this gradient of the upstairs stuff, and zeroed out if you are not making a false rejection. Okay, so this gets us an estimate of the gradient that we can use. That's not all we needed. We needed a confidence interval. And we needed not only a confidence interval, we needed a confidence interval on this whole term here, which is that true gradient with the dot product of a vector, and then maximized over the set of such distances in our rectangle. And the observation here that we're going to make in order to be able to do this is that this term here, which we're trying to maximize over, well, that soup is going to be achieved at some corner point of your rectangle. There are two to the d points. That's at least finite. So if for each of these different corner points, we consider making a confidence interval, we could take the union of them. And then this is going to be at least something with coverage 1 minus delta for the whole rectangle shape. Okay, in practice, we're not literally going to do this. We're going to be able to save computationally because rectangles are kind of nice, right? If your point is that you're expanding from, it's right in the middle of it, you can just look at actually where the gradient sign is positive or negative, and you'll know exactly which corner you care about. But how would you make one of these confidence intervals is the question. And maybe this is kind of a stupid bound, but it gets the job done, which is we have an unbiased estimator, and all you need is a variance in order to try to use Chebyshev Cantelli on this. And in fact, we are able to, using properties of the exponential family, we are going to be able to establish a bound on the covariance of that estimate of the gradient. This here is the Hessian of the log partition function. And I've written it here at this tau max. I require here that we have some upper bound on the sample sizes as well. That tells us we can't sample more than, say, 200 individuals from each arm of the clinical trial. If you have that, though, you can use exponential family and martingale properties to derive something like this. With variance and unbiasedness, you can get Cantelli. You can get an upper bound. You do that for one corner. You put it in your computer. It does it for all 2 to the d. And that's our second term. Checked off. And then the last term that we've got here, which encodes this sort of second order information. This we have to kind of integrate over the whole path from our expansion point and where we're trying to get in our rectangle. Fortunately, we don't need simulation to understand this. We just need some kind of nice uniform bound on the Hessian of the type 1 error function, and we'll be good to go. And the argument for this is not too dissimilar from exponential family moment identities, where if you were to write out the the Hessian of the likelihood for an exponential family, you get this kind of quantity here. You can make this sort of matrix inequality. And I don't quite want to make this, I don't want to say this is rigorous. I think to do this properly, you'd need to use martingales. But roughly speaking, sort of what's going on here is, that we are comparing then that integral of this quadratic form looking thing, and noting that this is going to be PSD, right? If we were to integrate over a larger set than the false projection set, we'd be computing the covariance of this sufficient statistic. And so you can drop it in, and roughly speaking, that is the upper bound. To make this rigorous, use martingales. There might be other ways to do it too. But again, we need here an upper bound on the samples we're going to take from every arm. There are other ways that you could get around this as well. And so I won't talk about those, but I do believe it's possible to lift that condition a bit further with some others. But this is, practically speaking, not that bad. In that, if you were to do this for a Gaussian, the bound that you get is, nicely convenient constant. At least if you shift, your mean around in space, this second order bound that you're getting is just flat, should be roughly the same thing everywhere. For other exponential families, it's going to be some analytic expression that you need to bound over a rectangle, but you can often just do that algebraically. Been able to do that in all the cases I've tried. Okay, so I've got a little demo here where we can break this down for a certain complex trial. Oh, yeah, right. I need to screen share. There you go. Is it working? No. Might need to stop the show. Okay. Popping up? Yeah, so this is for a Bayesian design. This particular one has 4 arms. What we've done here is we've removed 2 of the dimensions, and we're gridding out as our X and Y axes along the others for our unknown parameters here. We do have T1, we have, in this case, binomial outcomes, or so, really for each patient. T1, T2, T3, T4, right? We need to map this to the natural parameter space. Family. And these guys are fixed at small values in the null hypothesis. These ones are varying as the X and Y. And on the Z-axis, we have the family-wise error rate that we're upper bounding. And you can see here that there's some funny stuff going on. Well, what is this? Right here is our null hypothesis boundary for that arm, right? So there's a jump down right as we cross it. Something similar for the other guy. There's a hump in the middle. Why is that? Well, the inference procedure we're using here is a Bayesian multi-level model. And so as we take any small subset of 2 of these guys to be larger and larger, they're going to drag the others up. Which gives us this hump when they're plausibly pretty similar, although if you make them really, really clearly different from the others, the multi-level model just thinks, oh, these aren't so similar to each other at all. And we can visualize this in terms of these different components where our Hessian, the price we're paying for it, it's pretty small and flat, about 1% here. Here is our naive estimate of the gradient from Monte Carlo maximized over each rectangle, sort of component corresponding to that. This is the amount we're paying for the width on our confidence interval there. Here's our initial Monte Carlo simulation, and you can compare this to, we have a little bit of space here because this is actually not so large of a simulation. Okay. But these are our tools that we want people to be using to understand, validate complex procedures, particularly for, and my application is trial designs, where somebody's going to show up at the FDA with something that the FDA has never seen before, that they could handle it with these types of techniques, walk away with a rigorous proof and some visualization to tell you what's going on, and have that visualization also have some sort of guarantees about it. Okay, I can give more material on the area and the methods, but I actually do want to make sure we have enough time for questions.
How many simulations are these?
I think it's a pretty small number. You could tell by looking here that the height is about 1% is our standard error of the Monte Carlo. So I guess we could solve that, you know, square root p minus p over n is 5%, whatever. I don't know. It's a couple tens of thousands, maybe. Something like that. This might be my guess.
You mentioned in the middle that like one problem you have is that you're trying to verify that the trial works everywhere.
Yeah.
But you have, you know, hundreds of thousands of places to verify it. So even if it works, like just by chance, it might look like it doesn't work. Have you thought about coupling the different simulations? So like, you know, if you have location family, for example, use like the same randomness across the whole grid, so this doesn't.
We are doing this. And actually, yes. So these simulations across different points in space are non-independent.
Yeah.
And that's okay, because you know, we don't need them to, right? There's going to be only one of them that's really the true theta. So, oh yeah, I did want to show you guys more about the adaptive gridding that we're doing. Okay, so here I should do this in a better full screen mode. But you know, James did awesome at figuring out how to make this, you know, iteratively do sort of pilot simulations, decide, do you add more n, do you split out more grid points? And we're incorporating that now. Let me try to get back on the screen share. Just a second. Okay. Is that working? Good. Yeah, so you start off in the top left. Oh, I might need to. I can't locate my video anymore, but you know, we start on the top left, you know, iteration 0, right? Each time we decide we split into more points, or do we add more sample size? We do this iteratively a couple times, right? Okay, so it's branching more and more and more points. We reach, you know, a sufficient density that our Hessian term is not something we care about very much, and we're getting more error from the Monte Carlo part. Okay, so let's push that down. It decides to, you know, actually, we also have a stopping condition, by the way. And so actually for the vast majority of the points, it's just deciding to stop, right? We don't need to make it more accurate for those if it's pretty far away from you know, the boundary line where the type 1 error is going to be maximized. Okay, and then we keep going in these regions, right? And they slowly shrink as we, you know, basically, you know, figure out where we need more simulations, which is right along that type 1 error boundary, right along that H0 boundary, that is. Okay, and we can do the same thing in, you know, 3 dimensions. Why not? Same sort of algorithm. All right, you know, exploding point set, right, as it decides it needs to push down the quadratic, you know, part of the bound. It figures it out, right? We need more Monte Carlo right where that type 1 error is really close to, you know, 0.05. And it keeps adding more and more simulations there. I mean, technically, you know, it could go do an infinite number, right? If it is a truly, you know, exactly tight sort of situation. But you know, realistically, you just stop at some point and then tune back for conservativeness. These pilot simulations are not part of the proof, so you would want to run it one more time in a separate loop once you've figured out exactly the right sample sizes, if you wanted that rigor. Yeah.
The bounds you've shown is like for fixed inference procedure with fixed threshold.
That's right. Although the tuning is a layer that we can add on top, and the type 1 error like guarantee for the overall procedure is valid for the selected tune design.
So you don't have to like do a simulation to like find the threshold that like achieves the type of error you desire. Like can you use the same sample?
Oh yeah, so it is okay to reuse samples. Yes. So what you can do is you can, it is okay to correlate the simulations that way. Yes. And actually, sorry, I believe I require this. I require this monotonicity, that they are calculated on the same set of simulations, so that we do have this monotonicity property. You know, yeah.
So in the Taylor expansion, you know that like the error for like two grid points that are right next to each other should be pretty simple.
Hmm?
Do you use that as part of the simulations, or can you not do that because of the way
Yeah, I have not been doing that at all. For exactly this reason, I haven't even really tried too hard to think about it. I'm not sure exactly, yeah, in some sense, the Hessian is sort of trying to encode that, right? And then to the extent that it's failing to do that transport properly, right? I'm sure you could make it better somehow. But also, I don't know, just getting the sort of first thing and then letting Moore's law take you is pretty good too. I've thought about various ways of making this more complicated as well. You could do like importance sampling rather than in Monte Carlo. It was harder to get bounds for that, so I haven't focused on it really. You could probably up the efficiency quite a lot if you did that, but like not anywhere near as much as just like doing things on GPUs. So we'll keep it simple for now, but you probably could write a paper on that and beat us on a fixed problem that way. Yeah, so my hope is to use this for specifically trial design. And I have slides here, which this was just sort of extra stuff, but there are teams at the FDA which try to evaluate designs through simulation. Actually, they've started doing this. And on their list of problems for how do you assess whether a design is good enough or not to use, they say, how fine of a grid of simulations do you need? They're not doing it with this type of rigorous approach here. They're just simulating at a couple points in the null hypothesis set that they want to control against and calling it a day. I think there'd be really large advantages if we could make this a non-subjective process, right? Have it fully rigorized. Their process for doing this is lasts 240 days here, depending on how you count. They're really, really low throughput right now. And so, my thinking on this is if we could have software which people can just generally use to feed it in, they write a simulation of their design, right? It goes up to the cloud, we stamp it, send it back down. That could speed up the whole process of iteration, get these things out faster and usable in a wider variety of problem areas. Okay, I think this can also open up different types of trial designs as well. Like you could redesign your trial on the fly. Let's say you've gone through halfway to your first interim, you want to change things. There's something we use in this area, like the conditional type 1 error principle, that if you stay under going forward when you redesign, your new design has a type 1 error which is below, it's completely below the profile of what your old designs was from that point going forward. You'll overall still be controlling the type 1 error. Okay, so this also can let you do things like adding new arms unexpectedly to a trial, if you can frame it the right way, where you're you wind up sticking out another dimension, right, of your parameter space where up till now, everything had been constant in terms of how it's behaving. You now need to, do a whole process in order to validate the new design, of course, come up with it, make sure it satisfies these conditions, but I think it is in principle achievable. Limitations here, though, you need, dimensionality small enough, again, right? You absolutely do need to, believe in your model if these guarantees are going to be worth anything. And that is a very big problem in, clinical trials, particularly things like, cancer, oncology, or immune related things. Things are very hard to predict what's going on. And, there are these questions too about like what happens outside of your compact grid. And some people are just never going to be happy. I mean, we have these sort of forced contradictions here about different people's opinions towards these things. Talking with an FDA official who said they don't believe in priors, that people would not really get anywhere with those with him. Whereas I've come across a statistician that says they think the whole type 1 error framework is a waste of time. How they do things at Stanford, but it thinks it makes no sense and is a fake problem. I don't really believe that. There are some things I think we could do.
Is this an actual statistician or a
Yes,
simulated statistician?
this is actually. I do wonder whether he's easy to replicate with GPT-4 or something. But no, this is actually a prominent Bayesian statistician who was writing in response to being asked about this set of topics. So these are real people.
How did we get to be the bad guys?
I know. And it's not like we don't do Bayes at all, right? We do plenty. Well, maybe not enough according to some people, but I do hope that these sorts of things could let people use Bayes in places where you're not supposed to as well. Right? And maybe even get it through this FDA official if you can give him the right type 1 error properties as well. Okay. Thanks. Thanks.
So I proposed a long time ago these bias coin designs.
Hmm.
And
I'd love to analyze
I
that.
wondered if you could analyze them